Thank you very much, Shanice, and congratulations for your energy in setting up this group and managing it and starting to build that community of the next generation collectors. So I am a geologist, but in no way a mineralogist. My speciality is sedimentology, so depositional systems like rivers and deltas and submarine fans, nothing to do with mineralogy. But I have been quite fascinated by crystals since an early age as a hobby. And what this means is I'm not going to be giving you an academic lecture about crystals. So instead, what it's going to be is a series of stories that will illustrate a number of points along the way. And then the central point is I'm going to be encouraging people to get out there and play with making their own models. And it's fantastic to see Mark Holtkamp there because he's the author of a free web app called Smorf that makes crystallography fantastically accessible for anybody that wants to access it. He's shaking his head modestly. But it's really a wonderful time to actually just put your toes in the water. And the best way of learning is by doing. So the talk is going to be about using both virtual and physical models to help understand crystals. And if I move to the next slide, here's a first point of meditation and reflection. So crystals, I would say they're some of the most fascinating and beautiful natural phenomena on the planet. And I've put a picture of one there on the right. It's an anatase crystal, titanium dioxide. It's very small. It's about 1 millimeter to 2 millimeters across. It's from a famous locality in Wales called Prenteg. And the image is quite interesting because to make that image, I've actually shot 50 separate images focused at different depths and stacked them all up to make that image that's sharp from the front to the back. So something to reflect on is, as a mineral collector, what is it that you enjoy about, well, that one for a start, but in general, what is it you enjoy about minerals? And it's probably different for each of us. And some of the things that might be enjoyable in this case are the luster. It's brilliantly lustrous. The perfection, that's a crystal without any damage. It's got this lovely aesthetic contrast between the dark crystal and the white minerals in the background. It's got a famous locality with history attached to it. Some of you will be interested also in the photographic technique. And then you can see there's obviously symmetry there, isn't there? There's those four faces up on the top here. If you can see here's my cursor. And then there are these other four faces with striations. There are some other little faces down here. So there are different crystal forms. So for me, enjoying minerals involves all of these points here, but perhaps especially the last one. So if I'm presented with a crystal, I'll feel tension until I understand what all of those faces are. And a really good way of testing that understanding is to make a virtual model. And there's the anatase crystal on the left, and on the right is a virtual computer model that I've made with Mark's Smorf web app. And you can see it matches beautifully. The angles are the same, the relative proportions are the same. And now I can relax. The tension is gone. I know what those faces are. And there's another step, and we'll be talking about this later, how this came to be. But these days, you can make that virtual model and then you can also print it out. And that's really interesting to have in the hand because human ability to visualize in 3 dimensions from a two-dimensional image, I think it's very variable indeed. But pretty much everybody gets the same thing when you've got a 3D object that you can turn around and look at from different angles. So I'm going to be talking about how we make the virtual models on the left and how we can make the physical models on the right. And you can do that right now, actually. And here is the plan for the talk. So there are 4 sections. I'm going to start off with some context about crystal models and my 4 favorite moments in the history of mineralogy, each of which will illustrate a relevant point for the talk. And then the second section will be about making virtual crystal models. And then the third section will be about physical crystal models. And then the final and fourth section is about showing you some examples, some entertaining examples. And that's a really difficult one for me because I've got hours worth of examples. Within my eyesight here, there are various cabinets and there are lots and lots of stories I could tell. But fortunately for Shanice, there's going to be a lot of fluorite in these examples because that's her favorite mineral. And I believe the subject for the previous talks in this series. So there's going to be lots of fluorite. Um, all right, crystal models and history. So why am I showing you a chair in this picture? So I would direct you to the date on that chair, which is 1667. So that's the year that a brilliant Danish scientist called Nicholas Steensen wrote a paper on his dissection of a shark. And he had a good look inside the skull and the head of the shark. And he came to the conclusion that some unusual triangular stones that people called glossopetri are actually the fossils of shark teeth. And that has nothing to do with the talk today. But 2 years later, he published another paper, which is totally pertinent to today's talk. And I'm going to be showing you that. And it's actually a real pleasure to look at. So here is his 1669 paper. And you can see here he's called Nikolai Stenonis. It was very fashionable in those days to Latinize your name. And the paper is about solids within solids in nature, which is it's kind of very relevant to a lot of geology. And the picture on the right is pure genius. There are basically three segments. This is bottom interval here, which I already knew from sedimentology and stratigraphy. So this sequence of 6 time steps contains the four foundational rules of stratigraphy. And that would be the subject of another talk. So forget the bottom third. Up at the top, you can see there are various cross sections through crystals, and those make a point, which is crystal sizes, the faces of crystals vary, but the interfacial angles are always the same for the same kind of face. And we'll look at that in a bit more detail in a moment. That's the first law of crystallography. So you've got the four foundational laws of stratigraphy at the bottom, and you've got the first law of crystallography at the top. And in the middle are these strange shapes. And we'll get to those after we've looked at this. But this is really remarkable. And I'd looked at it in the past without quite knowing what it was. And it's actually rather wonderful. So these were his cross sections of quartz crystals. And you can see the first one there is pretty much a hexagon with a six-fold rotational symmetry. So every sixth of a turn, it looks exactly the same. This number 9 here is approximately two-fold rotational symmetry. Every 2 times you turn it, you get the same. And this number 10 is approximately a threefold rotation of symmetry. Twofold here, one-fold here. It's quite irregular. And his point was, yeah, so the actual crystals that you get in nature, they themselves have quite different looking symmetries, but the angles between those faces are always the same. And this is relevant to the kind of modeling that we're going to be doing. So we're actually not going to be modeling crystals in their irregular development of faces, but we're going to be getting the angles right, and we're going to be using ideal forms, and we're going to be getting, as you'll see later, relative growth rates approximately right. But most fun is this image in the middle. So, I wonder if you all looking at that will get it more quickly than I did, because I found myself quite slow to process what it was. And you can see that obviously it's something that's folded out that you would cut out and stick together. And what tugged at my memory were two things. So the first is these striated triangles up at the top, three of them at the top, three of them at the bottom. So obviously it's going to be something threefold rotational symmetry. And the other thing was these five-sided faces. And that brought back a really strong memory of a hematite specimen that I had as a kid from Rio Marina in Elba in Italy. And of course, I cut it out and stuck it together. And there on the left is what you get. So, as far as I know, the very first crystal model in that page of genius by Steno. And here on the right is an actual hematite crystal from Rio Marina in Elba. And you can see the light is highlighting that five-sided face that you can see here on the left, and the two unilluminated faces on each side of these two. So rather brilliant, really satisfying. And of course, I've printed this out, a bit of virtual model of it, and printed it out, and just over there. There were actually two of these models there. So fantastic. Steno was brilliant, a conceptual genius. So on this slide, I'm going to show you three other favorite moments. So the first one is 1781, 2 years before the end of the American Revolutionary War. And there is this mineralogist priest, or mineralogical priest, we might say, the Abbé Hoy, and he was visiting a friend of his, Jacques de France, who was a collector of minerals. And Jacques de France had a beautiful German calcite crystal in long prisms from St. Andreasberg. And he handed it over to Hoy. And then Hoy promptly dropped it on the floor, and it broke into a pile of cleavage fragments. So you can imagine de France looking at Hoy saying, "You idiot, what have you done?" But Hoy was really happy, and he looked down and he saw all the cleavage fragments and shouted out, "Tout est trouvé." Everything is found, kind of French eureka. So his brainwave was, all right, Steno, yes, the crystals grow with different size faces, so you don't get ideal forms. But actually, at a very fine scale, there is a very regular structure that can be stacked up to make the bigger crystal shapes. And the one I've shown on the right there, the little basic unit has been stacked up to show a scalenohedron, but it would also stack up to form the prisms in the beautiful specimen that he had destroyed. And after that, he set off with his little chisel, chopping up minerals, looking for cleavage fragments, and trying to understand what the basic unit was. Molecule intégrante is what he called them. And he probably had no concept of how small these really are, but an important conceptual step. And then the next one is 1912, 2 years before the beginning of the First World War. And it's a father-son pair of physicists called the Braggs, who were at Leeds, which is where I come from. And these two, they were holidaying out on the Yorkshire coast at a place called Cloughton near Scarborough. Good place to look for Jurassic fossils. And being on holiday, what do two physicists do? Well, they look at recent announcements from Munich University saying that there was a group of three that had directed an X-ray beam at a crystal and noticed that it diffracted the X-ray beam in different directions. And they were really excited by this. And young Lawrence, who was 22 at the time, he had the insight, do you know what's going on here? It's like reflection. And if you look at the little diagram there, so I've got, let me see, can I get rid of you lot? I've got all your faces over, over the diagram. But what you can see is here is the X-ray wave coming in and then interacting with a plane of atoms within the crystal lattice and then reflecting off. And it turns out that at just one, for a given spacing, there's just one angle of incidence and reflection at which all of those wave crests will align. So here, look at the second one down. You can see it's traveled further, but as it's coming back out again, it's got its crests, the wave crests are aligned. So what that means is when you found just that right angle for the spacing, all of those wave crests arrive at the detector at the same time. And you get a signal, you get an amplitude. Any other angle, you don't. They come in at different times, and there's something called destructive interference. And I've actually put an equation into this talk, which is a bit radical, but it's such a beautiful and useful one. I think it's worth actually seeing. So n lambda equals 2d sine theta. So everything there. The wavelength of the X-rays, it's pretty small. It's about 10 millionth of a millimeter. And you find the angle at which all of those wave crests align, and you do that by rotating. It could be the X-ray beam and the detector, relative to the specimen, or you can rotate one of the others, but you have to do some rotation till you find those angles. And once you've got those angles, you can find the actual spacing, which is genius. So now you can measure these very, very tiny spacings. So it's typically like I was saying, that kind of, well, similar to the X-rays, a little bit bigger. It's going to be a few 10 millionths of a millimeter, those distances. But it means that now, so as soon as that was understood and published, all in that same year, they were immensely productive, both the Munich lab and the Leeds double act. It Off you go. The rest of the mineral world, go and measure it, find out what are the different orientations in the crystal lattices and what are the spacings. Absolutely brilliant. And then my final one of these little moments in mineralogical history is 1937. So that's 2 years before the beginning of the Second World War. And there's a paper there by Donnet and Harker. And what they showed is that the relative importance of different crystal forms depends on which of the faces grows the slowest. And that depends on the spacings of the layers of atoms within the crystal. And now you've just seen from the one above there, we can measure those. You could actually work it out from theory to some extent, which they talk about a lot in that paper. But you can just measure them now when you know what that spacing is. So the ones with the smallest spacings are the directions that grow the quickest. And as we'll see later, the ones that grow the quickest give you the smallest faces or no faces at all. So if you know the structure, you can predict the forms. And here on the right, so why am I showing you a disco ball? And I mentioned to Shanice that there were going to be garnets. There will be garnets later in this talk. And I did this today, and it was a kind of daft idea. But that is a crystal model with every single orientation of crystal faces that I've ever met in garnets. Uh, and they're in a box up there to my left. And they've all grown at the same rate there. So they're all the same distance from the center, and they're all perfectly ideal. And what do you get? You see a sphere, don't you? But with lots of different colors. And do you find garnets like that? You do not find garnets like that. So what you find when you're looking for garnet crystals is the yellow faces and the brown faces. So that's a trapezohedron and a dodecahedron, and I'll be showing you those later. So this is really interesting for our model making as well. Which of the faces develop and why? So that's the typical shape of a garnet. That's my largest garnet. So this is what we call a trapezohedron, sometimes an icositetrahedron, and that's at the face of a dodecahedron. So not the multicolored, incredibly multifaceted, near spherical thing that I just showed you, the disco ball just now. And then one final conceptual thought here before we go into the actual modeling of crystals. So there are lots of different kinds of models that you can make. And over the past 3+ decades, I've made a very large number of quantitative models of the subsurface, but at much larger scales. And they can be looked at in two broad camps. So one where everything is in its correct spatial placement and the models have a scale, and you can actually use them for making measurements. And the other one that's on the right here, which is lovely that David is there because it's his crystal that I'm showing there. These are the kinds of model for understanding that we're going to be talking about today. So the one on the left, again, it's shooting X-ray beams at crystals, but in this case, at a much coarser scale. So I put the little crystal, it's a Tanzanian green grossular crystal. I put it on a little rotating table in an X-ray microscope. So it rotates 360 degrees. And then from one side, I shoot a beam of X-rays at it. And on the other side, I catch X radiographs, just like you would in a hospital. So one is snapped for small increments of rotation, and the software puts everything back together. And then you can interpret that 3D image. So that's what I've done here. I've got two things interpreted, the outside of that crystal group. And then in blue, there is this line of minute fluid inclusions. It's called a Farden. And I'll come back to this hopefully before the end of the year and get it published. but they're really fascinating. You can zoom right in and you can see the negative crystal shapes that are in there. Now on the right, so the one on the left, you can see it's got a scale there. There's a millimeter scale. So I can measure things there. I can measure the dimensions of each of those crystals. I can measure proportions as well. I can also measure angles between adjacent faces with the software. Now on the right, you can see here is David Eifel's beautiful beryl from Lundy. And he posted that on Facebook, and I thought that is very cute indeed. And my eye was drawn to these little tiny faces around the top there. So you've obviously got a prism, you've got a pinacoid, you've got a couple of pyramids, hexagonal pyramids over here. And then with Mark Holtkamp, whose face I'm looking at down there, with his app, I cooked up a model. So this model is, there's nothing measured there. I'm eyeballing, aren't I? I can see there's a prism, there's a pinacoid, there are these pyramids. So I've made this model probably in about 3 minutes. And here it is with the faces labeled. And then the model doesn't have any scale until I decide that it has a scale. And I scaled it up in this case ×5, printed it out and sent it off to David. So this is the kind of model that we'll be talking about, how to make this kind of thing. And as I said at the beginning, Mark's web app makes that totally accessible for anybody to get in and start playing and then just take it as far as you want. And we'll see how far we go. So that was section one. That was providing some context, some basic concepts around crystallography, the kinds of models that we can make, and introducing the kinds of models that we're going to make. And okay, how do we do it? We use smorf, which is what Mark has called the web app. And all you have to do is type in, and you can open up a window right now if you wanted to be actually following along, SMORF. And if you stop there, you will probably get a screen full of small blue cartoon trolls suggested to you. So do remember to put a .nl afterwards, and then it will take you right there. And what Mark's put in there is an immense library of crystal models. And many of them are from a remarkable set of atlases by Goldschmidt from 1913 to 1919. And there are other models that he's made himself.
Yep.
And the other thing that you can do there is you can make your own ideal models to explain the crystals that you've got in your hand. The crystals, you, Shanice, your most favorite fluorite crystals, you can make models of those. And that is my recommendation. Don't start with theory. Start with actually a beautiful natural phenomenon, something that you really enjoy, and then work away with that. At least I'm that way. Theory is boring until you need it to explain something. And there we can actually see Mark, of course. We can't actually see if he's got white hair there or not under the cap, but that's Mark with an ammonite in France. All right. So the next little bit is just about picking a really simple crystal, and I'll show you step by step how you'd make a model of it, and then tell you you're good to go. Because if you can do this, it will have shown you everything you need to know. So the crystal I've picked is this very common mineral from the small cleft mine in the Pennines, and it's a galena crystal. So if you look at it, you can see there's a square face on the top with some quartz crystals over the top. There's this triangular face here, which has got some truncations at each of its corners. And then there are another couple of square faces here. So that's what we're going to try and make. And the first thing to do, you type your smorf.nl. That's all you have to do. And this is what will come up. And the first thing is there is this massive library. So you can choose a mineral. And what I've done here is I've chosen galena because that's what we're going to be looking at. And then here you can see all the models that Mark has already got loaded up. And I've chosen just one of them, this one over here. And you can read the details. It says it's a twin on 111, which means it's an octahedron face. It's from England. You can find it in an 1857 book. Goldschmidt took their version from this. Tells you the crystal system and also the class, which we're not going to be getting into at all. But what you can see is it's a rather beautiful crystal. It's got the kind of faces that we were looking at in the actual one. Already you can see there's a square one. There are these kind of triangular ones with truncated edges. And it's also got this plane in the middle where the shape is reflected on each side of it. So that's the composition plane of a twin. And I love that because I haven't looked at that before, but I loved seeing that because I have a specimen that is almost identical. So this is from silver mines in Ireland. And if you look at this crystal here, you can see the twin plane or the intersection between the two halves of the twin. And you can see it's very much the same. And we'll come back to these, Shanice, using fluorites, debating, do we see this kind of twin in fluorites? Yes or no. But a really nice start. So you can always start here. Just go for a browse, take a look what's in there. And when you're making your own models and it's not entirely obvious what to choose, you can come and browse here to get some ideas. Um, so um, going back for a moment, down the bottom here, it says crystal drawing. If you hit that, it takes you into a new area where you can make crystals. And you choose your mineral, and then smorf will tell you what the crystal class is. And these are not very self-explanatory, these different crystal classes, but it describes the different symmetry operations for each of them. And it shows us what the unit cell is. And we haven't got any measurements here because it doesn't matter. It's the relative lengths that matter, and they're all the same. And there are three axes which are all at 90 degrees. So you can see those shown in the picture over there in the left. And in this case, the actual length of that cell is about a bit over 5.4 angstroms, so 5.4 10 millionths of a millimeter. But we don't care about that. We care about the shape of it because our models are, it's all relative. It's getting the shape right. And then if you come down here, you can see under forms, there are th three numbers there. I've got a one, a zero, and a zero. And I've got a number one here under distance. And these are the dreaded Miller indices that frighten a lot of people. But we're starting with this because it's quite easy to understand this one. So 100 means that the face that we're modeling here, it cuts only one axis and it's parallel to the other two. And you can see if you pick up a cube, that's true, isn't it? This face on the front here, it cuts across the A axis, but it doesn't cross the B and the C, does it? It's parallel to them. So you get a 1 and a 0, 0. So you type 100, that's what you get, a cube. Um, Now, our small cleft crystal wasn't just a cube, was it? It had those triangular faces on it. So here on that model, you can see that there are now these triangular faces. So you can see I've put another form in here, 1, 1, 1. So it means that each face in this form cuts each of the axes at 1 unit cell length. That's all it is. 1, 1, 1, nice and simple. And then the one here means that it's at the same distance from the center of the crystal as the cube. So it means that it grew at the same rate as the cube did. Yeah. And actually, in about 3 minutes work, we actually have got a model that mimics the small cleft crystal, like magic, really. Um, and you've got all these settings down the bottom here, so you can color things in. You can put the labels here. So these are the labels of the form. You could actually label each of these faces separately. So this one would be 100 because it only cuts the A, and that one would be 010 because it only crosses the B. But these numbers actually tell you the forms. It's all of the same kind of faces around your crystal. And now here's a question, because you remember I was talking about Donnet and Bellet, which faces grow quickest or slowest, and that determines the habit of the crystal. So the ones that grow fastest and at the smallest, which might seem counterintuitive, but if you're in smorf, you've got these sliders, and it's really beautiful because you could just slide them bigger or slide them smaller. Slide them. So what it's doing is taking the crystal further from the center than the neighboring crystals, but that's the same as growing faster. And next slide. So what have I done here? If you look here, I have now said that the octahedron has grown quicker than the cube, and it's ended up 1.4 times as far out from the center as has the cube. And what do we see? They're smaller, aren't they? The faces are smaller. So this is when they were the same growth rate, and this is where the octahedron grows more quickly and it's smaller. So this is one of those basic sliders for shaping the models to match your crystals. I'll show you later a bunch of kids in Malaysia in a museum open day where they were just playing with these models until they were happy, until they had a nice match, and then actually printing out the results as souvenirs. So we looked at two forms, very simple ones. So one was the cube and one was an octahedron. But galena can be quite a lot more complicated. So here, that specimen over here is beautiful, big, lustrous crystal from Wanlock Head in Scotland. And I'm turning it around to illuminate some of the little faces. So that's an octahedron there. That's a dodecahedron. And let's run it again. So octahedron, dodecahedron, and now I'm going to show you the little flat. You can see these very low relief faces here. So those are shown in the model here. And if you look over to the right, you can see I have added two forms. And what you've got here is a six. We have ones and zeros so far. So when you see a six or any number that's not a one or a zero, you have to remember that actually these Miller indices are reciprocals. So if you see a six, it means that on that axis, the face cuts across that axis at 1/6 of the distance relative to the others. So you can imagine it pulls in really close relative to the others and makes these low relief faces. So whenever you see something that's not a one or a zero, it's the reciprocal of the number that you see in there. And if you're actually tinkering away and you want to make a form steeper or flatter, that's what you would play with. All right. So that was the first two sections. So we've got some conceptual ideas. What I've just shown you is everything you need to start making models of crystals. And like I said, what I recommend is have the crystal that you're really fascinated by. Go in, choose the right crystal, choose the right forms, and tinker until it matches. And you'll tinker with the forms and you'll tinker with the relative growth rates. I'll show you this bit later. I'll show you my workings for a more complicated crystal. So, physical crystal models. Now, many of you will have seen sets of crystal models that have been made for several centuries now, and they tend to be just perfect, ideal, archetypal crystals to illustrate the different crystal systems, made out of different things, made out of wood, made out of plaster. Now happens to be the very best time, like I said at the beginning, to actually connect those virtual models that you can make using Mark's smorf web app with an actual physical model. And I'm going to tell you two stories before I show you some examples. And they're going to be slight detours, but none the worse for that. So this is my introduction to 3D printing. So I'm in Kuala Lumpur here, and on the left is a mesh or a set of meshes for the world's most completely preserved fossil coleoid. Coleoids are squids and octopuses and vampire squids. And I have the specimen, it's about 164 million years old. So I've done the same trick as I showed you with that green grossular crystal. Shone the X-ray beam at the specimen, rotated it on a rotating table in the middle of the machine, captured 360 frames, X-radiographs, used the software to compose a 3D volume. I've then gone in and I've interpreted the different bits of the vampire squid. So in pink is its body, in blue are its beaks, like the beaks of a parrot. In yellow is cartilage around the eyes. In pink here are its arms. And I then wrapped a mesh around it. It's a virtual mesh. It's like wrapping a mesh around an object, but you do it in the computer. And I had the thought, with that mesh, I should be able to print that. And I looked online, and there were places in Singapore that would print it, but they asked too many questions like how big, what material, what color. I don't know. So I went into a shop in Kuala Lumpur and they had 3D printers and they explained how to use them. And then I left that shop with the smallest 3D printer that they had. And that's what you can see here in the middle. And that's fresh off the press there is a 3D printout of this three-dimensional Jurassic vampire squid. And here in my hand here, I've just taken it away from all of its supports. Something remarkable that you can just pluck a complete uncompacted three-dimensional fossil from out of the rock, via a 3D image that you get in the X-ray microscope. So I had learned how to make 3D prints, but I hadn't remembered uh, or connected the idea of making crystal models with it. And this all started, this is a really funny story, and it's good that Mark's there. So started with garnets, and I had a really brief obsession with garnets. It lasted about a month. And it started in the summer of 2022 when I was in a taxi between Kuala Lumpur and the east coast of Peninsular Malaysia, heading off to do some underwater photography on a reef off the east coast over there, which was a great time for sharks as it happened. And on the way there, I was browsing, and on eBay, I saw this specimen here. And I thought, I have never, ever seen that. Those are, those triangular faces represent a form called a trisoctahedron. So sitting in the car, I doodled with Smorf on my telephone, um, doodled the model, which is here. And then I bought it, of course, because I'd never seen it before, so I bought it. And then with these two images, you can see there's this enthusiastic post to a Garnet Facebook group. And I can see I was really pleased here because I'd never seen it before. And they are rather beautiful. So after that, I looked for more weird garnet forms because I thought garnets were boring. I thought you only got them in the trapezohedron and the dodecahedron. And then with that, I realized, no, actually, they're quite a lot more interesting than I realized. So over the period of a month, looking on Etsy and eBay and a few other places, every time I saw a strange garnet with unusual crystal forms, I bought it. And then, of course, buying it made a crystal model of it. And this is what I found. So these are 16 different habits of garnet. And I've put them from common to rare at the bottom. And these on the left are just to show you what those forms look like on their own. So on the top row, you've got trapezohedron on the left, dodecahedron, and almost all garnets are some combination of these two forms. It's probably way above 90%. And then the next one is a hexoctahedron, which is that orange form there. And this is a Madagascar one. That's a Pakistani one. Sometimes you find cube faces. Vermont, that was a Chinese one. There's another Vermont one. Tetrahexahedron. So that's what a tetrahexahedron looks like on its own, um, which is kind of interesting. So the hexahedron part, well, we won't get into that. Um, but those are all the crystals showing that. The trisoctahedron that got me interested in the first place, that's the crystal from Afghanistan that I bought on in the taxi ride. And that's what it looks like on its own. So it's like an octahedron where you've got these three shallow faces. Um, and then rarest of all, an octahedron. So there are 16 of those. And then just because I'm keep on showing all these crystal models, I thought I'm just going to show you a gratuitous slide with actual garnet crystals because they are quite beautiful. Lots of different colors. This one at the bottom here, you can see the dodecahedron, the trapezohedron, and cube faces. Very unusual. This is the one with the trisoctahedron. That's the one with the hexoctahedron. Very lovely things. And then I had an idea, which was, all right, let's put all of the different ones that I've looked at over that month on a composition diagram. And this is what I found. So if you look at the end members of the garnets, spessartine, almandine, pyro. So these guys have all got aluminium in them. And that little group's often called pyralspite. And then there's a little group down here which have all got calcium in them. But the other ion varies, but from aluminium to iron to chromium. And that's often called eugrantite, that group. And indeed, all of these four over here are boring in terms of their crystals. They can be beautiful colors, but they're just the two forms that we saw earlier on. So everything from the dodecahedron to the trapezohedron. and all the freaky funky ones are down here, and they're between these two end members. So that was kind of interesting. And then browsing, this quite often happens to me. I find that somebody's already looked at that. So this Pabst, early Pabst paper had looked at that. And here he's gone and looked at the literature. So what are the crystal forms that are recorded for the different kinds of grossula, different kinds of garnets? And yeah, Mark Peach is blocking up the rest of the ones here so I can see grossula. So I said grossula. Um, so this, and here on the left, this is the rank order back to that Don A. Harker paper. Yeah. So they've got 6 here. And for the spacetine and the almandine, around 90% that he found are indeed of these forms, whereas the proportion is much lower for the grossula and the androlite, very much as I found. But actually, my collection here, I found 19 different forms rather than the 6 that are shown there. And this is the disco ball again. So this is what I made this afternoon, where I've shown all of those 19 forms, all equally developed, equal distance from the center of the crystal. So let's go back to March 2023. So you can see I've had fun with the garnets, not for long. So after that month, I never found anything new and forgot about them. But March 2023, I suddenly thought, hang on, I've 3D printed the vampire squid and a bunch of other things. Why don't I print myself out some crystal models? So I wrote to Mark, and this is my email, as part of my email on the 1st of March 2023. And I didn't ask, well, I asked him, how would I do that? And he said, well, from smorf, you can't um, um, you can't print out an STL file, a stereolithography file, but I can do it for you with his own program, Dexter. So I thought, great. But did I send him one to do? I did not. What I sent him were 16, those 16 models I just showed you. And I was thinking at the time, this is cheeky, because of course, from Mark's perspective, yes, somebody sends him 1 or 2 or 3. All right, I'll do it for him and send them back. But then, yeah, nothing. There was a period of quiet. There was no response. I was thinking, I have pushed my luck way too far.
Almost, yeah.
But maybe it was probably a good thing.
Yeah,
This is when you annoy someone, you're like, oh, come on, what is he thinking? Yeah, if it was a couple that do it, but no way am I doing 16. So Mark, being an exceptionally smart person, decides not to do them one by one. And what does he do instead? He makes a button that allows you to download the stereolithography file. So this is the 25th of March. So quite a bit of time has elapsed, but
yeah. 3 weeks.
nonetheless, there is a new button, download STL on the bottom right of the page. And everybody else can benefit from that. So it's my insolence and thoughtlessness that has led to this. But well, I'm sure you would have done it at some point anyway. But what that means is that absolutely anybody now, like you, Shanice, you've made a nice model of your favorite fluorite crystal. You can hit that button, and if you've got access to a 3D printer, you can just print it straight out and then have it next to your crystal. So that is why I'm kind of, you can tell I'm quite enthusiastic about the present moments in time. It's all super accessible for anybody that wants to participate in this aspect of crystallography. And I say, and away we go. So I have got loads and loads of these models now accompanying the actual crystal that has prompted the model in the first place. And I look at this and I realize I haven't got any garnets in there. And that's because they're in a drawer up on the top there. But and I couldn't grab them out of a cabinet for this picture. But there are lots of different models there, lots of fun to be had. And I said I would be showing you this picture. So this was a museum open day in Kuala Lumpur in November 2023. And this in the foreground here, this is my 3D printer, which is, because it's small, it's very portable. So I took it in, my laptop's down here somewhere. And there are various different stations in this open day, but in mine, Smorf was up. So these little kids that you see over there were coming by, making models, And I was helping them, of course, but essentially what they were doing was playing with those relative growth rates, that distance from the center, until they got nice matches with the actual crystals. And when they were happy, we'd hit Mark's STL button and then take it on a little SD drive, stick it on in the printer and hit print. And then about half an hour later, they'd come by and collect their souvenir models. And it was, I thought, something remarkable. These little kids are fearless. Whereas quite a lot of adults will see, Miller Index and think, oh, I'm not going anywhere near that, mate. But the kids are fearless, and as long as it's software that you can play with and it's visual, and you've got some understanding of what you can adjust, they were away and happy and creating and understanding. Um, and the one thing that was really exhausting was as we were making the virtual models, I had to keep my eye on the filament there because almost every kid that came by wanted to grab the filament. So I had to just kind of stop them because that would have wrecked absolutely everything. And I had this big poster for them there. So these are the seven crystal systems. And you see, you've got cubic, tetragonal, orthorhombic, trigonal, hexagonal, monoclinic, and triclinic. And on the right of each of these is a Malaysian mineral that illustrates each of those crystal systems. And in the middle is it's the stereolithography file, which is all directly ready for 3D printing. So yeah, we had a stack of models and which were gone by the end of the day. But from an outreach perspective, a really entertaining experiment and worth repeating actually elsewhere. All right, so those are the first three segments of the talk, and now we're on to examples. And I thought I'd come here because this was the very last time that I collected minerals in the wild myself. And it was an accident because this is not why I went there. So I went to this place to see the Norse Viking sites, uh, the settlement sites from about 1,000 years ago. And this is southwest Greenland. And I'm on a boat here, and you can see the amount of ice flow that is present there in the fjord. And so in this view, you can just about at the top see the endless ice and snow. And down here is the airport. So Eric the Red's farm from 1,000 years ago is just about here. And I was on a little boat coming down this fjord, Tunneljavik, and then looking sideways, and I had done no research whatsoever about the geology, but I'd found a little guidebook at the airport, and it mentioned the Illimausak igneous complex, which I knew from undergraduate days as a geologist. And that is hallowed ground for igneous geologists. And it's a bit over 1 billion years old. It's a magma chamber that was once several kilometers, 3 or 4 kilometers down below the Earth's surface, and now it's completely crystallized. But it's full of incredibly exotic minerals. There are tens of them which have been described here for the first time. So I was looking at that and then starting to look at where I was going, and I thought, so Narsak is where I was going. I started to think, actually, I've probably got time in a day to get up to the edge and then hike back down again. So that's what I did. So I hiked along here and then up this valley, and then zigzagged up here, which so we're right on the edge of the Ilimasak igneous complex here. And I actually packed a very, very small hammer just in case of interesting geology along the way. So I took that with me. And this is after quite a number of hours heading up that valley and then zigzagging up the side, the flank. And this is what it looks like. So it's like Lord of the Rings. It's like the portal to the dwarvish mines. So this is a mine portal. It's an adit that was excavated as a trial for uranium minerals. And actually, every rock you look at here is packed with crystals. It's absolutely remarkable. Um, and it was a strange day because I didn't see any other living mammal, let alone humans. I just saw some fox prints up here. And there were a few little birds. There were wheatears and buntings who I ended up speaking to because, there was nobody else. But really fascinating to find all the crystals. So I brought back quite a few. And as I do, as the habit is these days, I will make a virtual model for each of them. So these are minerals that are quite unusual: steinstrupene, eudialyte, narsarsuckite, and neptunite. And these are things I'd never made models of. They have quite similar trigonal crystals, which is interesting because they're very different. And some people will know these from Canada, narsarsuckite, in a very different habit, in a very tabular habit. And neptunite people will know from California, again in a very different habit. And here are the physical models of those virtual models I just showed you. So this is the neptunite, and that's the steinstrupene, and that's the eudialyte, and that's the narsarsuckite. And what I'm showing you here is my working for making that model. And it takes a bit of time. You've got to find the right faces. And then you have to play with the relative distances from the center, which is the same as the relative growth rates of each of those forms. And then I made this model, which really nicely matches the, you see that crystal there? You can probably see those faces. It's pretty small,
Yeah.
but really nicely matches. And then later I thought, let me go back to the Goldschmidt atlas just out of curiosity. And this was the Goldschmidt version of that crystal. And so I was kind of childishly delighted. I've worked this top one up, worked it out, and you can see it's a little bit complicated, but it's almost the same. He's got an extra face that actually, no, I do have it, but you can't see it from that viewpoint. It's down here. And some of the proportions are a little bit different. But it's rather beautiful, that, isn't it? It says Goldschmidt's one from the beginning of the last century. And this is mine from my trek up the valley there. And I'm just going to grab a few examples to show you now. So this I'll routinely have different northern pennines, barytes with the crystals up at the top. One funny thing recently, so as a kid, I had a very large barite crystal that looks just like this. And I bought it for £1 in the Merrion Centre in Leeds about 45 or more years ago. And it's just popped up again for sale. And its price has increased 1,000-fold in that time. So it's nice to see it again, but I won't be buying it. Um, and what's also nice is you can go back to some of the early literature. So this is Sowerby, 1804. And I feel a kindred spirit because there he is. He's got these beautiful illustrations of the barite crystals. And down at the bottom, he's got the corresponding models to explain them. So it feels like this kind of approach was commoner back then, back in the early 19th century, than it tends to be today. I don't know if others feel that, but it often seems to me that level of curiosity is not quite there these days. And this one I've put in for Shanice because she, in the promotional materials, she grabbed this from some Facebook posts. And it's from Cornwall and it's an apatite crystal. And you've got an idea of how my mind works now. So I'll see that and see there are lots of different faces and be quite intrigued by it. And that tension will be there. What are those faces? Again, I bought it. I can look at it up close. And here is the crystal model that matches all of those angles. And this has got 7 forms and 62 faces. I think it's probably the crystal I've got that's got the most faces. And here we have the thing that's printed out that actually lives with the actual crystal. Shanice, fluorite, your favorite. So once again, we go back to 1817 and Sowerby, another one of these brilliant individuals. So he's illustrated here some crystals of fluorite from Bir Alston in Devon. And there are other drawings down here which are very sophisticated. They're really, really sophisticated and beautifully complex for people that like the complexity. And what I've done on the left here is I have made models to match the main crystal here, the main specimen there, and these other crystals. So yeah, with a bit of experience, you'll recognize the cubes are obvious. A single bevel represents a dodecahedron. The double bevels are tetrahexahedrons. That triangular group of faces is a trapezohedron, and this is a hexoctahedron. So if you make those kind of models, you can slide the relative growth rates of each of them and make different shapes to make one form more prominent than another form. But lovely to encounter that in the early literature. And Shanice was telling me that she's extended from English fluorites into Irish fluorites. And here is one that I've published this year as part of a paper about a Chinese fluorite occurrence. If you look at it's from Ireland, from Larkin's Quarry in Ireland. And if you look at this picture up there, you can see it's quite complicated. It's a cube face on top. There are all these little reflective faces over here. So as usual, I've made a virtual model. And what this one shows is that sometimes during crystallization, the habit of the fluorite changes. So this one started off as an octahedron. And then as the precipitation continued, it started growing a totally different habit in crystallographic continuity on the corners of the octahedron, or the vertices of the octahedron, as you might say. And you can see it's quite complicated. Here's the cube, and then these little faces are hexoctahedron faces, and this is a dodecahedron face. And you can see that all of those over there. And then the octahedron that it's sitting on is over here. So if I play this, here is the physical model, which might be easier to appreciate than the 2D image, but very satisfying things. So that's a model that lives also with that specimen. Um, and this is a Northern Irish example now. So if you look at the crystal to the left, you can see it's got these colored points, hasn't it? So it's colorless in the middle, and it's got these colored points. And that means we can reconstruct how that crystal changed through time. So at the colorless stage, it was like this. So you've got octahedron faces, you've got the little dodecahedron bevels, and where those colored points are, we have a cube face. So as it continued to grow, this crystal didn't add any more to the octahedron faces, but it kept on growing on the cube faces until the cube was this little tiny relic. And that's quite difficult to explain because normally people will look at fluorite and they'll say, okay, starts off at high temperature, and then as the fluid in your pocket cools, it goes to a different preferred form, which is the cube. And this case, we have the reverse. So we've got quite a prominent cube early on, and then the late phase is the octahedron that dominates. So maybe the temperature went up through time as that was precipitating, or maybe it was something else. Because there's a point that I didn't actually mention when I showed the Donne and Harker paper, which says, look, just by virtue of the internal lattice crystal structure, some faces are going to be more prominent than others, which is true. But that forgets that in nature, there are lots of other things that can change. Pressure, temperature, pH, other contaminants, other solutes that are in there in the solution. And sometimes there are features that are temperature dependent. So fluorite, probably at the lower temperatures, there's probably adhesion of water molecules to the cube faces of the fluorite, which slows those down, which means that they're prominent, and the other faces grow out. So there's lots of different things that can happen actually in nature, and those can override the normal simple structurally defined relative importance of the different faces. And here, a Northern Pennines fluorite. And this is going to introduce the twinning example that I mentioned earlier on. So we saw that twinned galena crystal, and now we're going to talk about twinned fluorite crystals. So this is a favorite crystal of mine from Boltzburn. It's beautifully limpid, transparent. And so my model here is an ideal version of that. So you can see here we've got basically a rectangle, but here I've made it a cube. It's got just the same orientation as that. And the little line that goes through the middle, that's the twinning axis. So to make that twin, and it's easier to see with the one on the right, so I've put the twin axis vertical. So that's one of the corners of the cube. And if you look down the corner of a cube, you'll see that it's got a threefold rotational symmetry. It's got three faces that come together. So all you do is turn that cube round 1/2 a turn and intersect it with the original one, and you have that twin. And that's a penetration twin with a very, very simple twin law. Rotate it 1/2 a turn around a threefold axis, and that's what you get. And so Mark and I published this together in 2021 in the Mineralogical Record. And it was really, oh, it was provoked, but it was really provoked by a lot of dealers, especially labeling those, well, a different kind of twin we'll come to in a moment, spinel twins, which those are not, those are penetration twins. But this little detour here is, this is my very first venture into crystal modeling of twins. And I remember, this is 2013. I remember it well because this was a delicious Argentinian red, and that is Jarlsberg cheese. So what I've done is I've made a crystal out of cheese, and I've chopped it. I've cut it parallel to the composition plane in a twin, and used cocktail sticks as the twin axis, like you saw in that last one. Recommended. Anybody that wants to try that. All right, so spinel twins in fluorite. So the galena crystal I showed you earlier on was like this top one, wasn't it? This is a kind of twin that's been known for centuries and is very abundant in the mineral spinel, which is why it's called a spinel twin. And this kind of twin has got a plane that separates the two members of the twin, one above, one below. And there are a couple of ways you could describe it. So one is that that plane is a reflection plane. So the stuff above, the twin above, is reflected below. Exactly the same, but reflected. Everybody see that? And the other way of explaining it is that the crystal part of the twin above is rotated half a turn relative to the one below, but each side of the twin is kept apart by that plane. And then down below here is the classic, well, it's the archetypal penetration twin of fluorite, which we just saw with that Boltzmann example. And this top one is the archetypal example of a contact twin, where you have two sides that are in contact at a composition plane, as it's called. So as I was saying, for a few years, dealers in particular have been calling one type of fluorite twin spinel twins, and I have no idea where it started, never actually noticed, but this is the kind of twin in fluorite that they apply that to. So this is a big crystal it's a fist-sized crystal from Namibia, and it's flattened, it's hexagonal. And what's nice here, we've got some color coding. So the purple there represents a little dodecahedron face. So what you can see here is that there are different domains. So if you look at the two little ideal crystals down here, one of them is rotated half a turn with respect to the other. And in the actual crystal, that is also true. And you can pick it up from the purple dodecahedron face is being rotated 60 degrees, which is the same as a half turn. So we have two different crystal orientations intersecting, but with that top, that big hexagonal surface, coplanar, it's a shared plane. And it is an octahedron face. So it's a coplanar octahedron face. And on the lower left here, the yellow is that shared plane, the octahedral face, which is, so the two different domains, one domain rotated at 180 degrees with respect to the other. And you could already see these boundaries are very irregular. And in this little crystal on the right, it's also from Namibia. You can see how incredibly irregular those boundaries are. Yeah, it zigzags up and down and goes round, goes in, comes out. So whatever these are, they are not these spinel contact twins, are they? They're utterly, utterly different. And they have one feature in common, which is the half a turn rotation. So along the bottom here are specimens that I have in the collection here. So on the left is a penine twin, like the one we saw from Boltzmann. This is Chuma Bakur in Pakistan, Erongo in Namibia, Naika in Mexico, and this is a Colorado example. And understanding these didn't start with making the models. It started with holding the specimen and essentially looking around until I was familiar with the different faces. And then the thought experiment of, if I rotate this part 60 degrees, does it map onto the other part? And then I could see that that was the case in all of these. And so if we look on the left now, you can see here is that familiar Northern Pennines penetration twin. But these other ones have got that flat shared octahedron face, which looks really weird, doesn't it? It looks really strange. But of course, that is what happens when you do that half a turn rotation and your crystal actually has an octahedron manifest. And that is not the case in the Northern Pennines. We get cubes with some fancy modifications on the corners, but we don't get any octahedron faces. So to make it explicit, I've shown here the single crystals at the top with the twinning axis vertical. And then I've just rotated them by half a turn underneath. And then here we have intersected them. And you actually mimic all of the features of those twins. So these are all penetration twins with very irregular boundaries and not spinel twins at all. And this is just a virtual way of expressing that. So the back is an untwinned crystal. And like what I've shown so far, the vertical line there is the twin axis. And you've got a cube, you've got an octahedron, you've got a dodecahedron. Over on the left here, all I've done is spun it around half a turn, intersected. And in this case, I've flattened it, just like we see in the natural crystals. And that's perhaps because if you look at the edges, there are lots of angles, aren't there? There are probably more nucleation sites that would favor growing sideways relative to growing vertical. And then what I've shown on the right there is what you would expect if you had a spinel twin with a composition plane separating, half the twin above from half the twin below. So hopefully clear. And a really lovely collaboration with Mark there. Very enjoyable indeed. I'm gonna have a little sip. Final case study. So we're quite close to the end now. And yeah, Shanique's still fluorite. This was a remarkable find that didn't last very long. It was in 2023 in a graphite mine. And you can see up there close to the border with Russia. And some very, very strange fluorite crystals were observed and extracted quite quickly. And when the team that found them went back, it had been paved over. So there's a whole road there now that is paved over this location. So it was a very short-lived discovery, and therefore quite important that we document it. So I published this paper in Rocks and Minerals, and it came out after quite a long time in 2025. But here's a view of one of those crystals. And you can see it's like that Larkin quarry example that I showed earlier. You've got an early octahedron here, and then we have these very complex crystals grown at the vertices, at the corners. And they're a bit similar to the Larkin one, but it's a different hexoctahedron that's here. So yeah, here's the 3D model as before. The late stage crystals. So the habit changed through time, and the late stage crystals are dominated by dodecahedron, smaller cube. These are hexoctahedron, and these are trapezohedron. And just to show you some pictures, they're beautiful, aren't they?
Yeah.
Fabulously complex, and a little baffling at first. But these are the cube faces here and here. Doesn't look like a cube, but it is. These are the hexoctahedron faces. These are dodecahedron faces. These little stepped areas there, they're a different hexoctahedron. So quite complicated. And this is from the paper. This is all of the habits that we saw in the material from there. So pink are octahedrons, and then brown dodecahedron, yellow cube. Blue is one of the hexoctahedrons, green is another hexoctahedron. And all of these different patterns result from, just like I showed you when I was showing you that control on the distance from the center of the crystal in the virtual modeling, just varying those for the different forms until they match the crystals. And that's the variety that you see there. Really beautiful. And there's something, again, incredible, a bit like the Mourne Mountains example I showed you, where you can reconstruct how the crystal changed through time. And now we're just looking at the complex ones on the corners of the octahedra. If you look at this one here, can you see that there's a cube in the middle, but that there's more around the edge? And we can see here that at that stage, this was the crystal habit, cube, dodecahedron, octahedron. But the final stage looks like this. So cube, dodecahedron, and hexoctahedron. So the octahedron faces have completely gone. So what's happened here is that above the octahedron faces, it's grown out, but with this, so there's been no further growth on the cube, but there's been an infilling of the octahedron faces with this complicated pattern over here. And zooming in to show that in a bit more detail. So here you can see the late stage infills above the octahedron faces. And I've made another model here to make that clear. So at some point in the growth of that crystal, it stopped adding anything to the cube. Cube was stationary and all the growth was above the old octahedron faces. And then eventually, most of them, these two halves here of a dodecahedron face grow together. So it's in one way quite similar to a very traditional interpretation of a sequence through time with falling temperature. Start off with octahedrons at high temperature, then get cube and dodecahedrons at lower temperature. And then normally what we'd see in this position would be just cubes dominating at the low temperatures, like in the northern Pennines. But what we've got here is in common with those that we have the cube faces and they didn't grow out like we saw in the Morn example, but we've got this very complicated other group of things here. So there's something else going on there. And I would guess it's something to do with the chemistry of the solution there, that there are impurities that slow down the growth on these very rare faces, such that they are expressed in the crystal. So quite good fun, hey. Very, very beautiful, spectacularly complex crystals. And again, a reminder that nature can be quite complicated. It doesn't always follow these simple rules that we've talked about earlier. So that was the talk. And now we come to some conclusions. And those are the four areas that we talked about: crystal models in history, virtual crystal models, physical crystal models, and examples. And I've noted down some of the things that you might like to take away. So you remember there was Steno with his first law of crystallography. The habits are usually not ideal in natural crystals, but the angles between the faces are always the same. Then we had the mineralogical priest, Hoy, with his smashing of the beautiful mineral specimen of Jacques de France, and his intuition then that there is an internal regularity to the stacking, which can be stacked up to form different habits. And then Donne and Harker, that the internal structure drives the dominant crystal habits. But as we just saw in that last example, there are other factors that can override and give us really beautiful, complex crystals that you don't normally see, really unusual crystals. And we also talked about there are models for measuring and then models for understanding. And these next two sections were all about models for understanding. We're not trying to make exact copies of the crystals that we've got in our hands, but we're trying to make models that capture the right forms, the right relative proportions, and the right angles. So again, that point, and this should be the main takeaway. If you can remember that word smorf, all you need to do is type in smorf.nl to a browser and play, and you're away. And like I was suggesting, start with a specimen that you're curious about, that you really enjoy. And Mark has got a library of models in there to browse. You can make your own. Again, that recommendation, start with a specimen in hand. And if it gets a bit confusing, go back to the library for ideas. And again, the brilliant Mark Holtkamp with his STL button allows us to make physical models of these virtual crystals. And they're really good for outreach events because people can pick them up, they can turn them around, they can look at them. And sometimes for yourself, you've got the crystal, but actually the model really helps you understand it. Oh, here we go. And these were the examples I showed you. Greenland, because that was my last outing to go and collect things. Some British and Irish examples. Fluorite twins, and that 2023 Woolaga find. And that was the talk. So thank you very much for listening.